In this video, I am discussing KSET Mathematical Science previous year questions on real analysis topic functions of several variables. KSET 2018 question is let f from r squared to r be a function, be some function, then which one of the following statement is true? They are asking for a true statement. First option is if f is continuous at a point, then f has partial derivatives at that point. Second option, if f has partial derivatives at a point, then f is continuous at that point. Third option, if f has partial derivatives at a point, then f is differentiable at that point. Fourth, if f is differentiable at a point, then f has partial derivatives at that point. Okay, this is the question. Now, what is the concept behind this question? See, continuity of a function. If f of x comma y is defined at a comma b belongs to a comma b belongs to d is a subset of r square. This is a point ordered pair. Is a point of D common domain is a subset of R square and limit x comma y tends to a comma b f of x comma y exists and is equal to f of a comma b. Then we say f is continuous at a comma b, ordered pair a comma b, and we write it symbolically as limit x comma y tends to a comma b, f of x comma y is equal to f of a comma b. This is definition for continuity. Now, definition for partial derivative is let f from D is a subset of R, D is domain, be a function of two variables where D is open subset of R square, then first order partial derivative of f with respect to x at AB denoted by f of x a comma b or partial derivative of f with respect to x or else dou f by dou x defined as f of x means partial derivative of x, partial derivative of f with respect to x is equal to limit h tends to 0 f of a plus h comma b minus f of a comma b divided by h. This is definition for first order partial derivative of f with respect to x. Now, similarly, first order partial derivative of f with respect to y at a comma b is equal to partial derivative of f with respect to y at AB defined by limit k tends to 0 f of a comma b plus k minus f of a comma b divided by k. This is definition for continuity and first order partial derivative of f with respect to x and with respect to y. Now, result says or note result or note. First note is continuity need not. This is one need not. Continuity need not imply existence of partial derivatives. Continuity need not imply existence of partial derivatives. Example, see one example. F of x y is equal to mod of x plus mod of y. If x comma y not equal to 0 comma 0. 0 if x comma y 0 comma 0. Continuity at 0 comma 0. Test for continuity at 0 comma 0. Definition is limit x comma y tends to, here a comma b means 0 0 is there, a comma b, f of x comma y is equal to f of a comma b. This is definition for continuity. If you apply at 0 0, limit xy tends to 0 0, f of xy is equal to limit xy tends to 0 0, modulus of x, f of xy is modulus of x plus modulus of y. If x tends to 0, it becomes 0, y tends to 0, it becomes 0, therefore we get 0. Functional value is f of 0 0 here, 0 is there, therefore functional value is same as f of x comma y, therefore it is continuous. F is continuous here. Now, partial derivative. Test partial derivative or x comma. Test for partial derivative at a comma b means 0 comma 0. Partial derivative of f with respect to x. That means first order partial derivative of f with respect to x. F of, definition is f of x, partial derivative of f with respect to x a comma b is equal to limit h tends to 0 f of a plus h b minus f of a comma b divided by h. That means limit h tends to 0 f of 0 plus h comma b here 0 minus f of a comma b means 0 0 divided by h. If we put function is f of x comma y is equal to mod x plus mod y is the function. If we put b value 0, it gets 0. Therefore, h here mod h divided by h. Here modulus function for negative value, for less than 0 we get negative value, for greater than 0 value we get positive values. This is modulus function, graph for modulus function. Therefore, here we get two values for this partial derivative. Therefore, partial derivative not exist. Not exist. This one is sufficient for to prove partial derivative. Continuity need not imply partial derivative. I also try to find another one. Yeah, partial derivative of f with respect to y is, similarly we get plus or minus 1. In a similar way, this shows continuity does not imply existence of partial derivative. Continuity does not imply existence of partial derivative. Important note. This is very important. Next, Second note is existence of partial derivative need not imply continuity. This is note 2. Existence of partial derivative need not imply continuity. For example, see here, f of xy is equal to xy divided by x square plus y square if x comma y is not equal to 0 comma 0, 0 if xy is equal to 0 comma 0. Now, partial derivative of f with respect to x at ab here 0 0, limit h tends to 0, f of 0 plus h h comma 0 minus f of 0 0 divided by h. This is definition. Now limit h tends to 0, f of xy here, this in place of x, if we put h in place of y here 0, b value is 0 here, 0 divided by h square plus 0 square, functional value is 0 here, that means f of a comma b value is 0 divided by h. 0 into anything is 0, 0 into anything is 0, therefore whole value becomes 0. Similarly, we find partial derivative of f with respect to y at 0 0. We get 0. Therefore, partial derivatives exist. Partial derivatives of first order, derivatives of first order exist. Now, to check continuity for this function, to check continuity at a comma b. Definition of continuity is ab limit xy tends to a comma b, f of xy is equal to f of a comma b. Here ab is 0 0, therefore limit xy tends to 0 0, f of xy is equal to limit xy tends to 0 0, function is xy divided by x square plus y square along y is equal to mx, along y is equal to along y is equal to linear equation. This is y is equal to mx. This type along y is equal to mx, x tends to 0, here x tends to 0, here x tends to x value is 0, x tends to 0, y is equal to mx. If we put in place of y mx, x into mx divided by x square plus mx square. Take x square common, we get m divided by 1 plus m square. This is independent of x and y. This is independent of x and y. And also limit xy tends to f of a comma f of xy is not equal to f of a comma b. Functional value is 0 here, but we are getting m divided by 1 plus m square. Therefore, f of xy is not continuous. This implies existence of partial derivative need not imply continuity. This shows existence of partial derivative need not imply continuity. I write it. This shows existence of partial derivative derivatives need not imply continuity. Also, this using this, we can also generate one result, that is existence of, if a function is not continuous, then that function is not differentiable. We already saw in limit continuity and differentiability chapter. Therefore, third option, existence of partial derivative implied differentiability. Not correct. See, if a function f is continuous at a point, then f has partial derivative at that point. This is false. If f has partial derivatives at a point, then f is continuous at that point. This is also false, because we already checked. This is false. Now, if f has partial derivative at a point, then f is differentiable at that point. Here, f is not continuous, we get not continuous imply not differentiable. Obviously, no need to check this option. If we check this B option, no need to check this option because it is wrong. Fourth, if f is differentiable at a point, then f has all or false. Remaining one is right. This is f has partial derivative at that point. This is the right answer. Simple question. Result based question. Write down all result and practice. Next question. First one. If all first order derivatives of a function f x y exist and are continuous, they are saying continuous, and exist and are continuous in a neighborhood of a point, then f is continuous but not differentiable, not continuous, none. Using above result, comment your answer in the comment box. Try this question. Next question, KSET 2020, 11th question. Let f from r square to r be defined by f of xy is equal to xy divided by x square plus y square if xy is not equal to 0 and f of xy is equal to 0, f of 0 comma 0 is equal to 0. Which one of the following statement is true? D1 f of 0 0 is equal to 0. F is not continuous at 0 0. D2 f of 0 0 is equal to 0. F is continuous at 0 0. Before going to differentiability, first check continuity. See, and definition for continuity is limit xy tends to a comma b, f of x comma y is equal to f of a comma b. Here f of a comma b, f of 0 0 is equal to 0 is there. Limit x comma y, limit x comma y tends to 0 0, f of xy is equal to limit limit xy is equal to limit xy is equal to xy tends to 0, 0 here. X square plus y square is there. See, already discussed this question. They are given in 2021 along y is equal to along y is equal to mx. Here x tends to 0. Therefore, limit x tends to 0 x into mx divided by x square plus m x square. Limit x tends to 0 x tends to 0 x square into m divided by x square into 1 plus m square. This get cancelled. We get m divided by 1 plus m square. Here limit functional value is not equal to this functional value f of 0 comma 0. Here they given 0 not equal to m divided by 1 plus m square. Therefore, it is not continuous. But they given grace marks for this question. Why they given grace mark for this question? Comment in comment box. Grace marks. They given grace marks for this question. Why they given grace marks? Comment your answer in comment box. This is not. Answer is F is not continuous. F is not continuous. This is wrong. F is not continuous at 0, 0. Here, F is not continuous at 0, 0. But they given grace marks. Why they given grace marks? Comment in comment box. Next question. Let f of x comma y is equal to modulus of x y. Then f is differentiable. Option A, everywhere. Option B, nowhere. C, at 0, 0 only. Option D, everywhere except 0, 0. Also, comment for this question in comment box. This is the easy question. I need to check you understand or not. That's why. See, KSET 2024 question. Pick out these functions of f from r raised to 4 to r3 for which the derivative given by the Jacobian j over f will be 2x1 x2 x1 square 0 0 x2 x3 x1 x3 x1 x2 0 2x1 2x2 x4 square 2x3 x4 matrix into x2 square. Option given. First check theory behind this question. This is based on Jacobian of matrix. Jacobian matrix. Here, if u and v are functions of x, y, then partial derivative of u comma v with respect to x comma y is equal to first function dou u by dou x, partial derivative of u with respect to x and partial derivative of u with respect to y. Next, take second function partial derivative of v with respect to x, partial derivative of v with respect to y. This is theory behind our question. Now see here, this is 3, 4 matrix. 3, 4 matrix. Therefore, if you write this in linear transformation, we get r raised to 4 order tuple to 3 order tuple. Yes, that means it is like x1, x2, x3, x4 order tuples. This is u, v, w, u, v, w. U is a function of x1, x2, x3, x4. That means, right, do u with respect to x1, do u with respect to x2, do u with respect to x3, do u with respect to x4. Next, we write do v by do x1 and so on. This is do v by do x4. Next, do and so on. This is do v by do w by do x1 and so on. This do w by do x4. This type. This is a Jacobian of given matrix. Now they are asking for function. First, the differentiation of partial derivative of u with respect to x1. See, partial derivative of u with respect to x1 means 2x1. If we differentiate this, this is u. If we take u, v, w here, if we differentiate first function, we get 2x1 x2 square. We get first element as 2x1 x2 square. Therefore, it is wrong. We get first function as 2x1 x2. Next, check for the second one. If we partial derivative u, this is u, v, w. If we partial derivative u with respect to x1, we get here x2 is constant here, take it outside. Derivative of this is 2x1. 2x2 x1 means 2x1 x2. It is there. Next, check second one. Partial derivative of u with respect to x2 means we get this as x1 square. Here x3 is not there, x4 is not there, therefore this becomes 0, 0. Next, check third second row. That means v. Partial derivative of v with respect to x, we get this is x2, x3. Partial derivative of this with respect to x2 is x1, x3. Partial derivative of this with respect to x3 means x1, x2, x1, x2. Partial derivative of this with respect to x4 means 0. Next, check this one. This this one x1 2 partial derivative of w with respect to x1 means 2x1 partial derivative of w with respect to x2 means 2x2 partial derivative of w with respect to x3 means x4 square partial derivative of w with respect to x4 means 2x3 x4 there is an answer to check answer 2 x1 x2 x1 square 0 0 x2 x3 x1 x3 x1 x2 0 2x1 x2 2x1 2x2 x4 square 2x3 x4 2x3 x4 therefore it is the right answer. No need to check third and fourth. This is the right answer for this question. Simple question. Next question. If u is equal to x square plus y square and v is equal to x square minus y square, then the Jacobian partial derivative of u comma v with respect to x comma y equals, do and comment your answer in the comment box. This much for in this video. I hope this video is useful for you. If you like the video, hit the like button, subscribe this channel for more videos. If you want to practice more questions, join our Telegram group. Link is in the description. Check it once.